In 2008, an earthquake in Sichuan province killed 87,000 people and left 5 million homeless. Buildings crumbled, mountains split open, entire villages disappeared under landslides. Just 200 kilometers from that deadly fault line, in the neighboring province of Guizhou, people had lived for centuries trapped inside mountain valleys so deep and steep that the modern world could not reach them. Roads did not exist. Villages clung to cliffs. Families lived in caves carved into rock. A trip to the nearest hospital took 18 hours on foot, through trails that vanished in every rainstorm. More than 35% of the population lived in extreme poverty, isolated not by choice, but by geology that made normal life impossible. Then China decided to do something that seemed insane. Build more than 1,000 bridges across these mountains, many taller than skyscrapers, creating highways that float through clouds. The tallest, Dugue Bridge, hangs 565 meters above the river. That is higher than the Empire State Building turned sideways. Winds at that height reach 180 kilometers per hour, strong enough to rip steel beams loose, strong enough to throw a person off the structure in seconds. 12 workers died building these bridges. One mistake means an 8-second drop to the rocks below. No rescue helicopter can catch you. This is how China turned its most isolated province into the bridge capital of the world. Guizhou province covers 176,000 square kilometers, roughly the size of Washington state. More than 92% is mountains. Not rolling hills, but vertical karst peaks and canyons that drop 400 to 600 meters, straight down to rivers that carve through limestone over millions of years. 38 million people lived here, but before the year 2000, most were cut off from the rest of China. Villages perched on cliff edges had dirt paths as their only connection to the outside. Walking to the nearest market could take a full day each way. In the rainy season, which lasts 5 months, landslides made even those paths unusable. Farmers grew corn, potatoes, and rice in tiny terraced fields, but they had no way to transport crops to cities. Fresh produce rotted before it could reach buyers. Children who wanted to attend school beyond elementary level had to leave their families for months because daily travel was impossible. When someone got seriously ill, relatives carried them on wooden boards down steep trails, hoping to reach a road and a vehicle before it was too late. Many people died on those trails. The provincial poverty rate was 35% in the late 1990s, the highest in China. Entire generations lived and died without ever seeing a paved road. The Chinese government faced a strategic problem. Coastal provinces like Guangdong and Zhejiang were booming with factories, ports, and modern highways. Inland areas were stuck decades behind. If the country wanted balanced development and to lift hundreds of millions out of poverty as promised, it could not leave entire provinces disconnected. Traditional road engineering follows the terrain. Engineers carve switchbacks into hillsides, cut shelves into slopes, and wind roads up and down gradually. That works in gentle countryside. In Guizhou, it was a disaster waiting to happen. Canyons are too deep, slopes too steep. Following the terrain would mean roads with grades so steep, trucks could barely climb them. Turns so tight, buses would have to reverse to make the corner, and constant landslide danger from unstable rock. Even if such roads were built, they would be slow, dangerous, and expensive to maintain. Traffic would crawl at 30 kilometers per hour. Fuel costs would skyrocket. After studies that took 3 years and cost more than $80 million, engineers reached a conclusion. Do not go around the mountains. Go over them. Build bridges so tall and so long that highways can travel in nearly straight lines, ignoring the valleys below entirely. That decision created a construction challenge unlike anything attempted before. Building one record-breaking bridge is impressive. Building more than 1,000 in a single province over 2 decades is something else. The first bridge in the program, Beipanjiang Railway Bridge, opened in 2001 with a deck height of 275 meters. At the time, it was considered an extreme feat. Within 15 years, Guizhou had dozens of bridges taller than that. The province now holds 8 of the 10 highest bridges in the world. To achieve this, China developed systematic methods, reusable equipment, and trained thousands of specialized workers. Between 2000 and 2020, Guizhou invested more than $200 billion in transportation infrastructure, with roughly 40% going to bridge construction. The scale was unprecedented. At the peak in 2015, more than 50 major bridges were under construction simultaneously across the province. Every bridge starts with geology. Survey teams use helicopters, drones, and laser scanners to map canyons in 3 dimensions with centimeter-level accuracy. They identify potential anchor points on cliff faces, where rock is strong enough to hold the massive forces from cables and towers. On the ground, drilling crews bore holes 30 to 60 meters deep into the rock, extracting core samples. Geologists analyze these samples in labs, testing compressive strength, fracture patterns, and water infiltration. Rock in Guizhou varies wildly. In one spot, solid limestone can bear thousands of tons per square meter. 10 meters away, fractured karst riddled with underground rivers collapses under pressure. On early projects, several planned bridge locations were abandoned after core samples revealed unstable foundations. Engineers simply moved the alignment hundreds of meters to find better rock. For Guizhou Bridge, the survey phase alone took 14 months and required 470 boreholes drilled to depths averaging 45 meters. The team extracted and tested more than 12,000 kilograms of rock samples before approving the final tower locations. Once the site is confirmed, construction begins with foundations. Giant excavators and blasting crews carve horizontal platforms into cliff faces, often 300 to 500 meters above the valley floor. Workers drill rows of foundation piles, each 10 to 15 meters deep and 1.2 meters in diameter, directly into the bedrock. These piles are filled with high-strength concrete mixed with steel rebar cages weighing up to 8 tons each. For Guizhou Bridge, each tower required 32 foundation piles arranged in a grid pattern. The total volume of concrete poured into these hidden roots was 11,000 cubic meters per tower. On top of the piles, crews build massive anchor blocks. These are reinforced concrete structures weighing up to 15,000 tons that will grip the main cables of the bridge. The anchor block on the Guizhou side of Guizhou Bridge measures 24 meters long, 18 meters wide, and 14 meters deep. Steel anchor rods, each 300 millimeters in diameter, extend from the cables down through the block and into the rock piles below, creating a connection capable of resisting pull forces exceeding 50,000 tons. The most dramatic construction moment comes when the first link crosses the canyon. At heights of 500 meters or more, traditional methods like boats or temporary towers are useless. The solution is a helicopter. A heavy-lift helicopter, typically a Russian-made Mi-26 or a Chinese Harbin Z-8, flies slowly across the gap with a thin pilot rope trailing beneath. The rope is only 12 millimeters in diameter and weighs less than 1 kilogram per meter, but it is strong enough to handle 500 kilograms of tension. Ground crews on each cliff use high-powered radios and laser rangefinders to guide the helicopter. Wind is the enemy. At these heights, gusts can swing the rope by 20 or 30 meters horizontally. Pilots must hover at precise altitudes while the rope dangles through turbulent air currents. On the Guizhou Bridge project, it took 4 attempts over 6 days before weather conditions allowed the helicopter to successfully pull the first rope across. Once the thin pilot rope is secured on both sides, workers use it to pull progressively thicker cables. The 12-millimeter rope pulls a 25-millimeter rope. That pulls a 50-millimeter rope. Eventually, a heavy-duty cable thick enough to support machinery is stretched across the void. This temporary system, called the catwalk, allows crews and light equipment to travel between the towers during construction. With the catwalk in place, the real load-bearing cables can be built. For suspension bridges like Guizhou and Guizhou, this means spinning massive main cables from thousands of individual steel wires. Specialized machines ride back and forth on the catwalk, laying each wire along the exact, calculated path with precise tension. Each wire is 4.5 millimeters in diameter, and a single main cable contains over 15,000 wires bundled together. Workers spend months guiding these machines, laying wire after wire, until the cable reaches its final diameter of nearly 1 meter. The completed cable on Guizhou Bridge weighs 4,800 tons per side. That is the weight of 40 fully loaded Boeing 747 airliners hanging between 2 mountains. The cables must handle not just the static weight of the bridge deck, but also dynamic loads from heavy trucks, temperature changes that cause steel to expand and contract, and powerful wind forces. Every cable is wrapped in protective layers of galvanized steel and weatherproofing compounds designed to resist corrosion for at least 100 years. In Guizhou's humid climate with frequent rain and fog, corrosion is a constant threat. Inspection systems built into each cable allow sensors to detect early signs of rust or wire fatigue. While cables are being installed, tower construction happens simultaneously. Bridge towers in Guizhou reach staggering heights. The towers of Pingtang Bridge stand 332 meters above their foundation, taller than the Eiffel Tower. These are not simple vertical columns. They are complex engineered structures designed to handle compression forces exceeding 100,000 tons while resisting winds, earthquakes, and temperature extremes. Crews pour them in segments, climbing higher every few days using hydraulic formwork systems that attach to the structure and lift themselves up as new concrete cures. Each segment must align perfectly with the one below, because even a 2-centimeter error at the base can result in a visible lean at the top. Concrete is mixed on-site to exact specifications and pumped up through pipes inside the tower. A typical segment requires 300 to 400 cubic meters of concrete, which takes 12 to 18 hours of continuous pouring. Workers cannot stop in the middle, or the concrete will cure unevenly and create weak points. During hot summer months, when temperatures exceed 35 degrees Celsius, crews add ice to the concrete mix to control curing temperatures and prevent cracking. In winter, when temperatures drop below zero, they use heated blankets wrapped around fresh concrete to prevent freezing. Tower construction on Pingtang Bridge took 26 months, working around the clock, with crews rotating in 8-hour shifts. Once towers and cables are ready, deck installation begins. The deck is the part drivers actually use, and it must be positioned with millimeter-level precision despite hanging hundreds of meters in the air. For large bridges, decks are built from prefabricated steel segments manufactured in factories and transported to the site by truck. Each segment on Guizhou Bridge weighs between 80 and 120 tons, measures 12 meters long, and contains a complex internal structure of steel beams, cross-bracing, and attachment points for suspender cables. Specialized cranes mounted on the towers or traveling along the main cables lift these segments into position one by one. Workers standing on the partially completed deck guide each piece using hand signals and radio communication. The segments are connected with high-strength bolts, each torqued to exact specifications and welded at critical joints. As more segments are added, the deck grows from both tower sides toward the center of the span. Engineers continuously monitor alignment using laser tracking systems and GPS units accurate to within 5 millimeters. Temperature affects everything. Steel expands in heat and contracts in cold. A 1,000-meter span can change length by more than 30 centimeters between winter and summer. The final closure segment, installed in the center, must go in at a specific time of day when temperatures match the calculated ideal. On Guizhou Bridge, the closure happened at 6:30 in the morning, when the steel temperature was exactly 15 degrees Celsius. If they had waited 3 hours, thermal expansion would have created a gap impossible to close properly. Conditions during construction are brutal. Winds at 500 meters can gust to 180 kilometers per hour with almost no warning. Weather in these mountains changes fast. Clear morning skies can turn to dense fog in minutes, cutting visibility to less than 10 meters. When fog rolls in, all work stops, because workers cannot see their own hands, let alone position massive steel segments accurately. Rain turns every metal surface into a slippery hazard. Workers wear harnesses attached to safety cables at all times, but the cables themselves can only do so much. In high winds, standing on a narrow steel beam is like standing on the wing of a moving airplane. The structure sways. Your balance is constantly challenged. One wrong step, and the harness is all that keeps you from falling. Over the 2 decades of bridge building in Guizhou, 12 workers have died in falls, 3 were killed when a crane cable snapped and dropped a deck segment, and 5 died in vehicle accidents transporting materials on narrow mountain roads to construction sites. For every completed bridge, there are injuries. Broken bones from slips, burns from welding, crushing injuries when heavy equipment shifts. The safety record has improved over time as procedures tightened and equipment advanced, but building highways in the sky remains one of the most dangerous construction jobs in the world. Under the road surface, Each bridge contains hidden systems that keep it functional and safe. Steel crossbeams and diagonal bracing connect the two sides of the deck, preventing twisting when crosswinds hit. Expansion joints at both ends allow the structure to grow and shrink with temperature while keeping the road surface smooth. In Guizhou's climate, where winter lows can reach -10°C and summer highs hit 38°C, a 1-kilometer bridge can change length by 40 centimeters over the year. Dampers installed at strategic points absorb vibrations and prevent resonance. Engineers learned from deadly bridge failures in other countries where wind-induced oscillations built up until structures literally shook themselves apart. The Tacoma Narrows Bridge collapse in 1940 is studied obsessively in Chinese engineering schools. Every bridge in Guizhou includes multiple vibration damping systems, some passive using heavy weights and springs, others active using hydraulic cylinders controlled by computers that respond in real time to movement sensors. Drainage is critical. Heavy rains can dump more than 200 millimeters in a single day during monsoon season. Water that pools on the deck adds weight and creates dangerous driving conditions. Drainage channels run along both edges of the roadway, feeding into vertical pipes that drop water into the valleys below. On some bridges, these drainage pipes are over 500 meters long, and the water reaches the ground moving fast enough to create a visible spray. Before any bridge opens to traffic, it must pass load tests. Engineers park columns of fully loaded dump trucks on the deck in carefully calculated patterns to simulate maximum traffic conditions. For Guizhou Bridge, this meant 132 trucks, each weighing 49 tons, for a total test load of 6,468 tons, concentrated on the main span. Instruments embedded in the steel and concrete measure how much the bridge deflects under this weight, how the cables stretch, and how forces distribute through the structure. The real behavior is compared to computer predictions made during the design phase. If the match is close, the design and construction are validated. If there are surprises, engineers have to figure out why. On rare occasions, load tests have revealed problems that required additional reinforcement before the bridge could be approved. Dynamic tests come next. Engineers drive trucks across at various speeds, brake hard, and accelerate to see how the structure responds to moving loads. Sensors record vibrations and oscillations. The goal is to confirm that traffic will not excite resonant frequencies that could cause fatigue damage over decades. Only after weeks of testing and hundreds of data points do authorities give final approval for public use. The transformation these bridges create is difficult to overstate. Before they were built, a trip from Guiyang, the provincial capital, to the city of Xianxi took 7 hours winding through mountain roads. Now, it takes 90 minutes on an expressway that crosses 12 major bridges. A farmer in a remote valley who once needed 2 days to bring vegetables to market can now drive there in 45 minutes. Fresh produce that used to rot before reaching buyers now arrives in perfect condition. Hospitals that were unreachable for most residents are now accessible within an hour. Tourism has exploded. The same cliffs and canyons that once trapped people now attract millions of visitors who come to drive across bridges that seem to float in clouds and to photograph views that look like scenes from fantasy films. Between 2000 and 2020, Guizhou's poverty rate dropped from 35% to less than 2%. Average household incomes tripled. The provincial economy grew faster than the national average for 15 consecutive years. Roads and bridges were not the only factors, but they were the critical foundation that made everything else possible. This was not just about building impressive structures. It was about using engineering to solve a fundamental problem of geography. Mountains had kept millions of people isolated and poor for centuries. Conventional solutions were too slow and too expensive. China chose to go over the mountains instead of around them, and to do it at a scale that seemed impossible. More than 1,000 bridges in 20 years, dozens of them breaking height and span records, the tallest standing 565 meters above the water. Highways that now carry 2 million vehicles per day across terrain where no road existed before. The cost was high, over $200 billion and 20 human lives, but the result rewrote what mountains can do to people.